Good morning, everybody, and welcome to the first class after the time has changed. I know some of you probably didn't set your clocks, and that's why you're not here. You probably need to watch this one recorded later on. One thing that one of you sent me a message about the videos that are on Canvas, not updated, and I apologize for that. And I mentioned that before in the past that it's a good idea to actually subscribe to the YouTube channel. That way you will get the content right away. I mean, they have been lingering in there for quite some time. Today I updated them, and hopefully this will not happen, but actually to guarantee this for you guys from your end, it's better actually to subscribe to the channel. And that way you will get the videos up front. Sometimes what happens is I start the process and I get in the middle of something else, and it takes a long time to actually put them on YouTube. So by the time they are there, I forgot to go and change things and do things, or I'm busy doing other classes and so on and so forth. Okay. Today, we're actually starting a new topic, Chapter 40. Chapter 40 is also part of Exam 2. So I think we're sticking this to the original schedule in terms of the exams, in terms of the content. So chapters 37, 38, 39, and 40 are part of Exam 2, and the rest are part of Exam 3. So this, we're not changing anything in terms of the content for this class. You will see that you will have enough materials for an exam by the end of this unit, by the end of Chapter 40. So anyway, let me share with you the screen. So last time I remember when we were at the end of Chapter 39, because here is a story basically that is emerging from those two chapters. Particles and waves, they behave mutually. A particle can behave as a wave, and a wave can behave as a particle, depending on the experiment you're conducting. So the wavelength usually, or the momentum of the particle, if it were a wave, is going to be h over lambda, and the wavelength is going to be lambda over h over p. So take the same expression basically and move it around. The energy in general, in this case, is going to be proportional to the frequency, with the constant frequency, the constant proportionality being that Planck's constant. So this is basically in a nutshell from the two chapters. In addition, and it's very important, you have the Heisenberg uncertainty relationship, which relates the momentum in one direction, the momentum in one direction with that direction itself. This being greater than or equal to h bar over 2. H bar, just to remind you, is just h over 2 pi. It's the same constant, h, and h is 6.626 times 10 to the negative 34 in the SI units. Namely, it's going to be joule second. So this is basically in a nutshell what we have come up with. Obviously, there is another similar relationship that connects also the energy to the time, and because those are complex, these are conjugates, not complex. These are basically related to one another in a similar fashion. That too also is true. So these are the Heisenberg uncertainty relationship, Heisenberg uncertainties. And I know probably you might suspect that this have to do with statistics, but they are not statistical in nature. They are inherent to the problems themselves. So it's not just because I cannot really measure precisely the position and measure precisely the momentum. That's why I'm getting this uncertainty. No, it's because of the nature of these problems. And probably if you take quantum mechanics down the road, or physics down the road, you will delve a lot on this topic, on this point in here. A word of caution for the lab. There will be a lab on these things in here. So the delta of any quantity, Q, is usually measured as the root of the average, or the, what is it? The RMS of Q, and also the average of Q. Okay, the root means square, so you're going to take the square root and you're going to basically find the squares and take the average of those squares and then take the square root. We're going to get into a little bit more details about this point once we get in. So the point being in here is this relationship that relates the momentum and the energy. We looked at it in terms of the wave number. The wave number, by the way, and the wave length are related to one another, just like the period t and the omega. Omega is equal to 2 pi over t. Okay, and 1 over t is the frequency, so this is the 2 pi f. So this is basically stuff that you've learned a long time ago. So in other words, we could express these same relationships in terms of the wave number, which is this one, and also in terms of the angular frequency, omega. So the way that works is usually the momentum then becomes clearly equal to h over 2 pi times 2 pi over lambda, and this is k, and this is your h bar. So this becomes h bar k. The same thing for the energy. The energy is equal to hf. All I'm going to do in here, divide by 2f and 2 pi and multiply by 2 pi. This becomes your omega, and this becomes your h bar. So this becomes h bar omega. In other words, these are the relationship of the momentum p with the wave number, and also the energy in terms of the angular frequency. The reason why this is important is because we know a wave satisfies this equation. The second derivative of that term that describes the wave is equal to a constant, which is usually, in this case, is going to be written as the speed, because it's going to have the right dimensions as a speed. I'm sorry, I put it backwards. So this is not the derivative with respect to time, it's the derivative with space, okay? Is equal to the derivative with respect to time. The second derivative. So why I'm not writing in here? Because fill in the blank. In the case of a string, you have y. So the string goes up and down, and the y describes its motion up and down. So you plug in y in here for the string. In the case of electric field, you take the electric field that oscillates up and down, and you put E in here instead. In the case of the magnetic field, you put the same thing. The magnetic field is going back and forth, and you're going to plug in B in there. In the case of sound, you're going to put the pressure, for example, that is the change in pressure for the sound that you did in physics 1. So you plug in the pressure in here as it varies with the sound moving in the air, in the calm air. So you put P in there, or you put the density of the air, because the air is compressed and relaxed as sound is propagated. So you're going to put that in there, or actually you put the chi, the displacement of the entire bundle of air as it's moving back and forth for sound to propagate. So this is similar expressions for all of these terms. For a case of drums, you're going to put the surface of the drum in here with coordinates that are in whatever your choice of coordinates. Usually Cartesian coordinates don't work well, so you're going to use, if it's a spherical shape, I mean a drum, not spherical, circular shape, then you're going to use polar coordinates for it. So whenever problem of waves, fill in the blank in here, okay? So I'm gonna take generic term in here, one of them, doesn't matter which, I'm going to take y, and this is basically what y is, okay? One particular case from all of the solutions is the plane wave. And the plane wave, or a planar wave, has a characteristic which is of cosine and sine. So it's a times cosine of kx minus omega t plus b times cosine of the sine of the same thing. There is a phase usually. So this is a case of a wave that is traveling in this direction. For a wave that is traveling in the opposite direction, it's no big deal. All you have to do is change the minus to a plus and you're done, okay? So this is where your wave number is. It's scaling the factor x. So it has the dimensions on 1 over length. And sure enough, it has a dimension of over length because it's 2 pi over lambda. Okay, and lambda is length, is wavelength. And omega, which has radians over second. So what matters in here is the second. The 2 pi and the 2 pi are just to make sure that this is in radians of some sort. It doesn't matter the 2 pi in here, just their scaling factors in there. Anyway, the point being in here is this is the expression for the wave that you have seen time and again. Okay. So what you do in this case, you take the first derivative of this expression with respect to, it doesn't matter, let's take it with respect to x. So we're going to pull a k in here and flip the sign. So it's going to be minus k times a sine of kx minus omega t. And in here it's going to retain its sign. So it's going to be plus k times b cosine of kx minus omega t. You do this one more time because you need the second derivative. So you do the second derivative with respect to x. Of course, t is considered constant in here. And we're going to put another k in here. So it's going to be k squared with the negative sign. So it's going to be negative k squared times a, and then the sign flips to a cosine, kx minus omega t. And this will flip the sign from a cosine to a negative sign, but you're going to pick up another k in here times that k. So it's going to be another negative k squared times b times sine of omega t minus b, kx minus omega t. Okay, the big deal in here is that negative k squared is multiplying the sum. So negative k squared times a cos whatever stuff plus b times sine whatever the same thing, which is kx minus omega t. I'm just getting tired of writing it, so I'm putting the parentheses and you can fill in the blank if you like. Now, this is y itself. This is what we started with as being y, a cosine plus b sine. So this becomes minus k squared times y. So this is the second derivative with respect to x. Let's do the same thing with respect to t. So since we have space in here, we're going to do it in here. So the derivative with respect to t is going to pull me a minus omega. I'm sorry, where is the, here. We're going to pull a minus omega first, and the cosine will become a minus sign. So a minus times minus is going to be plus omega times a, and the cosine flips to a sine of the same stuff, kx minus omega t. And this will pull a minus omega, and the sine becomes just a plain cosine. So it's going to be a minus omega times b times cosine of the same stuff. Okay, we're going to do the same second derivative with respect to t. We're going to pull again another from the sine. Remember, the sine has a kx minus omega t. We're going to pull another minus omega, and the sine becomes a cosine. And omega times omega is omega squared, but don't forget the minus that came in from this expression. So it's minus omega squared times a, and the sine flips to a cosine of the same stuff. And in here, we have, remember, a minus omega that's going to come out, and we have a cosine that's going to flip to a minus sign. Minus times minus times minus is going to be a minus again, because there are three of them now. Omega squared times b times the sine, because the cosine changes to a sine, and everything is the same. In a similar fashion, I'm going to put minus omega squared, but I will have an a times cosine plus b times sine, and that is exactly what I started with. This is y. So this is also minus omega squared times y. So if I go back into my original equation and replace the second derivative by minus k squared omega, okay, minus k squared y, and I have on the other second 1v minus 1 over v squared times the second derivative with respect to time, and that's going to be minus omega squared y. Obviously, the y cancels, and the reason why it should cancel is because I'm not looking for y equals to 0. Y equal to 0 is a trivial solution to the wave equation, and that is not actually a wave. That is the string in its unperturbed state, or the electric field non-existent with the magnetic field. So that is basically the there is no electromagnetic field in that case, or the calm air where there is no change in pressure or density or anything, or in the case of whatever wave, when you have y equal to 0, when you have that term equal to 0, is not a wave. So we're not going to concern ourselves with that. We're looking for the case where A and B in the same time are not equal to 0. So one of them can be equal to 0, but not both. So in that case, y cannot be 0. So we can cancel with respect to it. Of course, I'm going to cancel with respect to the negative sign. And at the end, I will end up with omega squared equals to k squared v squared. And this is exactly the dispersion law. Its square root in this case is going to be omega equals to kv. Omega cannot be negative, but k can. The reason why k can is because if k is negative, you have a cosine of a minus minus, which is a cosine of a plus. And you will have a sine of a minus minus, which is just a minus, where that minus can be absorbed in the constant b, and that is going to be describing the other wave. So one of them, which can I write omega kv, is for this one, and this one I can write just on negative kv, and that's it. And it's the same relationship. In terms of magnitudes, I can write both of them to be omega equal to kv, in absolute value. Obviously, this is the same expression that we've used all along, namely for light, for example, V is equal to C, K is 2 pi over lambda, omega is 2 pi F, move lambda to the other side, lambda F is equal to C. So this is exactly the same relationship that I kept on calling dispersion law that we use time and again. So this is true for waves. However, this is the problem now we're facing. Let me explain. For our case, we're going to take a free particle. We are not really having this type of waves at all. We have a different kind of waves. So we want to describe our free particle with a wave. The reason why we have to describe it by a wave, because of this relationship that we started with that keeps on popping up in both chapters 38 and 39 to explain the range of phenomena, from the photoelectric effect to the Compton effect to the scattering to all kinds of things that are involved with this phenomenon, both for electrons and both for photons, basically. We want to describe it by a wave because it exhibits the wave patterns. There is constructive and destructive interference for waves. But also we want to explain it in terms of particles because it also have energy and momentum. So we want to have both words, basically. We want to have the two of them at the same time working for us. So here is the case. The simplest case that we can start with is a free particle. That means that its energy, E, is entirely kinetic energy, meaning that the potential energy is equal to 0. Free, meaning that there is no potential energy. It's away from everybody else. So this isn't its entire kinetic energy, its entire energy, which is its kinetic energy. And for a particle like this one, its energy is just 1/2 of mv squared, or 1/2 of m squared v squared divided by m. And this is the momentum of the particle, squared, of course. So the energy of this particle is p squared over 2m. So this is how we want to think of this particle as being free. On the other hand, this energy also must be equal to h bar omega if it were going to have a wavelength. I mean, if it were going to have a frequency. hf and divide by 2 pi, multiply by 2 pi, and it's back to h bar omega. The p, though, must be related to the wave number through this relationship, the one that we showed. It's h over lambda multiplied by 2 pi and divided by 2 pi, and it becomes h bar over k. So the relationship that we really need for this expression is that h bar omega must be equal to h bar squared k squared, that is with the momentum, divided by 2m. This is a dispersion law that we need. I mean, you can simplify by h bar if you care, but this is in a nutshell what we want to see. This is the expression that we want to see in here. Okay, let's see here if we can do this. We're going to have a wave. So at this point, I don't know what letter to use, honestly, because we have Y, we have E, we have B, and we don't even know what kind of wave these particles do. So we're going to give it a name psi, okay? So we're going to describe the wave behavior of the electron, of the particle. We're concerned, honestly, more with the electron right now because that's most of the experiments that we did with the function psi. So psi, and I'm trying to write it as capital psi now, is a function both of x and t. Okay. Since it's a wave, I'm going to write it as a cosine of, again, kx, where that k is the same k in here, minus omega t, plus b sine of kx minus omega t. So this is the wave this is the part that is going to describe that wave behavior, okay? If I take the derivative with respect to time of this function psi, I did that already for the previous y. So all I'm going to do is pull out minus omega from the first one, and times minus, so it's going to be a plus a omega times the sine of kx minus omega t. And in here, we're going to put out another minus in here, and that's the end of it. So it's going to be minus b times omega cosine of kx minus omega t. That's it. And that's what we need. We need just an omega. We cannot go the step further to omega squared. That is really not what this expression is talking about. It's talking about just simply about omega. So I cannot really push this derivative to another stage in terms of the time derivatives. But I can do the time derivative twice. I mean the space derivative twice, I'm sorry. So the space derivative of psi with respect to x twice, I'm going to do it quickly in here because we already did it. So I'm going to pull minus k squared times a times omega. No, I'm sorry, there is no omega. I'm sorry. We did just. And then you have the cosine kx minus omega t. And in here, we're going to put minus k squared again. What did I do in here? I'm sorry. This becomes a cosine. And this is the term side. That's when we take a derivative once, it's going to be a cosine. Take a derivative again, it's going to be a sine. And we're going to pull a minus k squared again. So it's going to be minus k squared times b times sine of kx minus omega t. Somehow, these two terms with the scaling factors h bar omega must match. So I'm going to multiply this one by h bar everywhere because I need it from this side, h bar omega. And I'm going to also multiply this term, it has k squared in it, multiplied by h bar squared over 2m. So I'm going to come to this expression. Why did I do squared in here? I'm sorry. Just multiplying by h bar both sides for the time component. This is the one that I need to multiply by h bar squared over 2m, both sides. So it's going to be h bar squared over 2m, because this is a relationship that I'm shooting for. I'm shooting for an h bar omega, and I already have my omega on this side. All I'm doing is multiply the entire expression by h bar to pull the h bar omega out. And then I have a k squared in here. So I need to multiply that k squared by h bar squared over 2m to get that stuff in here. So I'm matching this expression here. I'm trying to shoot for it. So when I pull an omega in here and equate the two, of course, I have to make them equal because that's what this expression is saying. So I'm going to pull the omega out, and the first term look like this: h bar omega times open parentheses. I'm left with an a, of course, and I have a sine of kx minus omega t minus b. Of course, there is a problem in here. And let me tell you what the problem is. I'm not saying that this derivative and this derivative are equal. I need to have a scaling factor, actually. I need to make these two expressions equal with, remember the fudge factor that we did in relativity, that gamma that at the end get as a correct behavior? The same thing in here. I need to have a fudge factor in here. We're going to call it C, because that's how it's always called. I hope you guys don't confuse it with the speed of light. So this is some sort of a fudge factor, just like what we did with the gamma the other day, just to make sure that this relationship somehow works. So we really need a scaling factor in here, okay, to make everything works. So I'm going to multiply this expression by C and then impose a condition that we know. So again, so On this side, I'm not going to mess around with it. So it's going to stay the same. So it's minus b times the cosine of kx minus omega t. Because if I do that, that expression is satisfied, because on the other side, I have h bar squared over 2m times k squared, which is common to the two. So I'm going to take it out with a minus sign, by the way. The minus sign also can come out. So it's going to be a minus h bar squared k squared over 2m times that fetch factor times the c that we need to adjust to make all of this work, times of course what is left inside, it's just a cosine of kx minus omega t plus b sine of kx minus omega t. Okay, where this terms are here, just from the second derivative with respect to space. Obviously, we did the whole purpose of this exercise just to make sure that this is true. So what we're saying in here, that this relationship is true. So we can cancel with that term. And we have to match now term by term. The sine term has an a in front of it on this side. On the other side, it has, here is the sine term. It has a b times c with a minus sign. So this two must match. So what I'm saying in here is a must be equal to minus bc. Because the sine and the sine must cancel, because those are time and space dependent, and they can vary from place to place. The only time that they are going to be identically the same is they have the same coefficients all along. So a and negative bc must be true all the same. Same thing with the cosine. This term also changes from place to place, and it could be anything in here from time to time also. So for it to be an identity all the time true, all you have to do is just say minus b on this side must be equal to minus ac, because it's an ac on the other side. So this is what we ended up with. If we find a c that makes this true statement, then we are in business. Then we have an equation that works for us. So the first equation says a equals to minus bc. Well, the second equation is just b equals to ac, that's all. All I'm going to do is sub the value of a in the second expression. So it says b equals to a, and a is minus bc times another c from here. That's minus bc squared. All I did was just use a substitution. So I sub this value here. Okay. Obviously, we don't want b to be 0, because if b is 0, a is 0, and we're back to no wave again. We don't want that. We want b that is not equal to 0. B cannot be equal to 0. That's it. Because if b is equal to 0, this is an identity. But if b is equal to 0, so is a too, because from the first equation. So no matter what fudge factor you're going to come up with, you're not going to get an equation, because both of them are going to be identically 0, and this is a no back to no wave at all. So b cannot be equal to 0. That means that c squared is equal to -1. That means c itself is an I. Okay. Or a negative I. Typically, we take it as a negative I. And I will see why, okay? Because when you move it to the other side, it's going to be just the I in here. I could have multiplied this one by C instead. Anyway, and that's going to give me the positive energy that I want in here for all of my problems. So what I'm going to do in this case is sub the value of C in this equation. Since it's in here, I multiply C by both sides, okay? And the expression that I'm going to end up with is I multiplying this term, so I'm moving it to the other side. So it's going to be I times the spatial time h bar first. Don't forget that h bar that we needed in here, times the second derivative of psi with respect to time. I mean, the first derivative with respect to time is equal to again, you have the second derivative with respect to x Okay, hold on a second, okay? Let me, because I want to make sure I have the right convention for the sign in here. Because we're doing it in representation that is a, yes. So it's a minus h bar squared over 2m times the derivative of psi with respect to x, the second derivative with respect to x. So this is the equation that we ended up with if we choose the correct sign for c squared. I mean, I moved it to the other side, so I must multiply by it. That's why the sign in here, you have the minus that is coming out of the front of the x squared in here. So this is the equation that we must use. For a free particle. The problem that immediately pops up is that this is a complex equation. That is because of that I. You guys did complex numbers, didn't you, in your math classes?
Yes.
Okay, so this is a complex equation. So that means psi itself must be complex, because here is the problem. If psi has a real part and an imaginary part, so if psi, I can write it as a real part of psi plus an imaginary part of psi, with the I adjusting that term. The first side of the equation, when I multiply by I and take the derivative, so h bar is just a constant. When you take the derivative of everything in here, I will take the derivative of the real part plus I, the derivative of the imaginary part. Once I multiply by I will, this becomes real, becomes a negative, whatever that time derivative with respect to of the imaginary part. And this becomes an imaginary because I'm multiplying by I. Must be equal to a constant in here times the second derivative of psi with respect to x. And this second derivative of respect to x is going to pull me the second derivative of real part with respect to x. So let me explain this with the actual thing. So I'm going to take this with respect to t and multiply it by I h bar. So this is going to be an I h bar, the second derivative with respect to time of the real part, minus h bar, the second derivative with respect to time of the imaginary part of psi. So that shifts the I from the imaginary to the real when you multiply by it. When you do the same thing for the other side, it's minus h bar over 2m times the second derivative of psi with respect to x. Now this doesn't shift anything. It leaves everything in the same location of the real part. And then you have on the other side minus I h bar squared over 2m, the derivative of the imaginary part with respect to x. Now, the difficulty in here is that I have to match two complex numbers. So the real part must be equal to the real part and the imaginary part must be equal to the imaginary part. Here is what that means. That means the imaginary part with respect to time is related to the second derivative of the real part with respect to x. And the derivative of the real part with respect to time is related to the second derivative of the imaginary part with respect to x. So this is unavoidable. Using complex numbers is not a choice, is a must for this equation. You cannot somehow isolate all of the problems and leave the real part and say, okay, we're going to solve this problem somehow for complex numbers, but as a trick, and then at the end, we're going just to pull the real part. That's not going to work. You have to treat the entire psi as an imaginary part, as a complex function. So psi is complex. That's what this equation is telling you. So somehow this wave has to have an interpretation because it's not real. You cannot plot a complex function. You cannot work with it. As a matter of fact, this is probably the safest bet in here, trying to work with it numerically. So if you're going to solve the Schrodinger's equation, this is, by the way, Schrodinger's equation for the free particle. If you're going to work with Schrodinger's equation at all, whether free or no free, and you have to use a computer and you're going to program it yourself, most likely this is the easiest way to deal with it, and that is to have two equations to solve at the same time, at least for the 1D problem. For the 3D problem, we're going to end up with 6 because the problem gets complicated, and that is for a single particle. For multi-particles, is the problem get multiplied by that many particles. Anyway, this is a complex function, psi, and we have to interpret it somehow. Before I interpret it, let's fix the issue when it's not free. A particle in a potential, a non-free particle. Basically, what I'm saying is the energy is somehow the kinetic energy plus a potential energy. That's it. So that's what we're saying in here. Note the following. For this equation, this is a temporal behavior. This is where the potential energy p squared popped up. So this is actually the entire term in here is just the potential energy for the free particle. If the particle is not free, all we have to do is adjust that term with the potential. So this is how we're going to make that assumption, that for a particle not inside not free, then I'm going to have the first term I h bar, the second derivative of psi with respect to time, that's it, I don't expect it to change, is equal to the kinetic energy contribution, which is just this term, which is minus h bar squared over 2m, not 2m squared over 2m, times the derivative of psi with respect to x, plus a contribution of the potential, plus u, which is typically a function of space, u sub x times psi itself. So this is the equation that we ended up with. So in other words, this is a stretch, if you wish, of the free particle to the case when it's not free. Since we recognize that this is the kinetic energy, then all we have to do is just add the potential energy, and that's it. So this is now becomes Schrodinger's equation in general for the one-dimensional case, of course, namely psi. It depends only on x and t. The reason why we call it one-dimensional is because we're not doing a relativity, by the way. T is not a dimensional variable in this case, just a parameter for time. So it's just the x in here that describes the position in space. So this is Schrodinger's equation in general. And for the 1D, of course, for 3D, we're going to have a derivative with respect to y, derivative with respect to z, and derivative with, that's it. I mean, in addition to the derivative with respect to x. So this is Schrodinger's equation. And this should solve our problem. This should address the issue of how to describe a particle behaving as a particle and a wave at the same time. The only trouble with this is that we ended up with a complex function that we need to interpret somehow. We need to give it an explanation. And that is due to Mr. Max Born, who basically noted the following. Any wave, the ones I described above, all of them, doesn't matter which. When you do an experiment on them, whether a Young experiment, it doesn't matter which experiment you do, for the standing waves, it doesn't matter. What you really are measuring is the intensity or the energy of the wave. And the energy of the wave is proportional to the square of the displacement. For this one, it's proportional to the electric field. As a matter of fact, if you guys remember, it's 1/2 of the maximum value. That's the amplitude of the electric field times epsilon naught. For this one, it's 1/2 times B max squared over mu naught. For this one also, it has to have with the maximum pressure or the maximum density displacement or the maximum displacement of the air. All of them, all of this quantity squared, by the way. So what Mr. Max Born basically suggested is the following, that this function then, if I take its amplitude squared, that should give me the probability of finding the particle somewhere in space. But of course, this is being a complex number. In order to find its amplitude itself, the amplitude of this complex function is equal to the complex conjugate times the complex number itself under the square root. In other words, the square of this amplitude is just the product of the complex conjugate times the complex number itself. Does this make sense to you guys? Is this what you did with complex numbers? Do you guys remember this expression or not? From complex numbers?
I don't remember that part.
Yeah, I mean, for those who need a refresher, if I take a complex number z, which is x plus iy, of course, the amplitude is just z equal to of this complex number is square root of x squared plus y squared. And this can be thought of as a product of this complex number z by its complex conjugate, where we change the sign in front of the I to negative I. And now if you multiply these two numbers by themselves side by side, z star times z, x times x is x squared, minus I times plus I, that's minus I squared, and I squared itself is minus 1. So minus I squared is positive 1. So it's going to be positive y squared. And the cross terms cancel. X times minus iy times plus iy times x, they cancel, and you end up indeed with the amplitude. So this is some basic properties of complex numbers. So the amplitude of this term in here is just a complex conjugate times the complex function itself, okay? Having said that, that means that then the probability of finding a particle between x and x plus dx is piece of x is equal to psi squared times dx. In other words, it's psi star times psi times dx. So this is really what this means, that the function itself tells me the location of the particle. So if somehow I draw this function psi squared as function of x, this is the amplitude squared. This is not, this is the amplitude squared. This is the actual amplitude of the complex number psi. And so if I draw this function, for example, it looks like this, then most likely the particle is going to be near where this function is maximum. Not as much near here, but probably more so than in here than the other locations. So this is what this function is saying. So what the psi squared itself is actually a probability distribution. So psi squared itself is a probability density. Probability density. It's not an exactly probability by itself. In order for me to make it into probability, I have to ask, where do you want me to find it? Between this two gap, between this delta x, then I can tell you, integrate over that span of space, and I tell you with what much of probability I can find it. Provided, okay, and this is a very important thing, provided that psi is normalized, and I will explain what that word means. That means that psi itself, when I square all of the probabilities, I should find 1. That means that if I integrate from negative infinity to positive infinity of psi squared dx, it must give me 1. That means I'm 100% sure the particle exists somewhere. That's what this statement is. The particle exists somewhere. If I am sure of that, then this can be interpreted as probability density. Of course, if I find 7 in here, let's say I don't find 1, all I have to do is absorb that 7 back into the definition of psi. In other words, rescale it, okay? And then I will end up with 100%. You guys understand what I'm saying? Let's say, for example, psi turned out to be this function. C times some other function, let's call it chi, okay? Where chi is normalized. So what I say in this case is psi squared, of course, psi squared is going to be C star, C times chi star chi I'm assuming C is a complex number because everything from now on it's a complex number. So what ended up being in here in this case is C squared chi squared. Well, this is just going to be normalized when I integrate over infinity. So this is going to be from negative infinity to positive infinity of psi squared dx is equal to C squared times the integral of this function itself. This is 1. I assume that this function is normalized. So this is not 1, but rather C squared. So I'm going to define it back inside the other one. In other words, divide by C squared, and I have now a renormalized basically function side. So in this case, the condition is that if I know for sure that the particle exists and it exists somewhere, and I add up all of the probabilities of that, that means I will end up with 1. This is all of the probabilities when I sum from negative infinity to positive infinity. So I know the particle is somewhere on the x-axis. So in that case, then this becomes a probability density. So this is the interpretation of Mr. Max Born for all of these things in here, okay? Otherwise, like I said, we're dealing with a complex number that we need to somehow interpret, because that's exactly what happened when we did the double slit experiment. Let me go back into the double slit experiment to see what that means. When we do the, or single slit, it doesn't matter which one to take. So if I have an opening in here and another one in here, and let's say I send photons, light, first of all. Light is going to produce this nice maxima and minima, this kind of a bright and dark fringes. So this is dark fringe, this is bright, dark fringe, bright, then a dark fringe, and so on and so forth. Okay, so the point being in here is, what I'm measuring in here? I'm measuring the intensity of light. And the intensity of light is really proportional to the square of the amplitude of this wave, whatever that is. So if it's an electric field, it's proportional to the electric field. If it's a magnetic field, it's proportional to the magnetic field squared, maximum value actually squared. And if it's a combination of the two, it's just the sum of the combination of the two. And at the end, there is a relationship between B max and C max. If E max, if you guys remember, it's E max over C. So there is a relationship between these two. So it doesn't matter. If it's light, this is what we're doing. Same thing. If I send a beam of electrons now, not light, from both sides in here, I'm going to produce the same pattern. So what should I be measuring? I am not measuring psi, I'm measuring psi squared. So this is the distribution of psi squared now. And when I'm integrating over a span of time, I'm going to get where this max values are going to be. So at the end of the term in here, this is going to show that integral because you're going to sum through it. So this is, in a sense, the interpretation that has to do with the square amplitude. So this is, now we have a full picture. If we're going to describe the wave behavior of particle, we have to solve Schrodinger's equation. Once we find the solution, we have to impose this condition on it to normalize it. And then once it's normalized, then look at the probability density. Where it's max, that's where your particle is. If you want to measure any quantity, let's say, for example, the position of the particle, x on average. So what you do in this case, let's use x on average. So what I'm going to do in here, I'm going to multiply psi star times x times psi integrated over dx from whatever span that I want to find, from negative infinity to positive infinity. So this should give me x, the average value of x, of this particle. If I want to find the average value of x squared, I do the same thing. X squared, this is related to the lab, by the way. Negative infinity to positive infinity, provided psi is normalized. X squared psi dx. If it's not normalized, that's the point I was trying to argue earlier about that C, divide by the integral from negative infinity to positive infinity of psi star psi dx. That's it. Okay. If it's normalized, you don't have to, because you're dividing by 1. If it's normalized, you don't need to because it's 1. But if it's not normalized, you divide by it. That's all. So if you want to find the momentum, for example, of the particle, P, on average, you really have to integrate from negative infinity to positive infinity against psi star p psi dx, and that's the end of it. If it's not normalized, you divide by that integral from negative infinity to positive infinity of psi squared, or psi star psi. So this is in a nutshell, full explanation. Of course, any term in here, if you want to find the average energy of a particle in this case, you do the same thing. The average energy of this particle from negative infinity to positive infinity is going to be psi star times that term now, p squared over 2m plus u times psi dx. Remember, p squared now has to be interpreted as a negative h bar squared times the second derivative of x divided by 2m, of course, and then psi plus u, okay, times psi. So that's the only thing in here. Okay, this is an introduction to quantum mechanics. If you guys are going to delve into it, you're going to find far more in detail in there. And this is the reason why I'm mentioning this last few points, is because they are related to the lab. From this point on up to here, actually, all of this stuff in here is related to the lab, because you're going to be given certain functions, psi, Gaussian distributions, all kinds of psi's in there, and you're going to do these calculations. Okay, it helps to have an integral table. It helps to have something to calculate those things like Mathematica, and to get these things going for you, because it's going to be a long calculations if you really have to do this integrals on your own. Okay. Other than that, I think the lab asks that you guys, if you can have access to, I forgot the name for it now. It's a SHAM, basically series of integrations tables. Okay, that's the old days, because we didn't have access to electronically tools nowadays. Okay, so we got into a lot of details in here. Okay, about these things in here. So any questions so far? Okay, let me tell you what happened, okay? We came up with Schrodinger's equation. We really did not, we came up with some sort of a proof for it, but we're going to make it as an assumption from this point on. We're going to assume that Schrodinger's equation is the basis. It is your F equals to MA, if you wish. It's not, it is, if you will. It is actually your F equals to MA when it comes to quantum mechanics. So it's the foundation we're going to build all of our stuff in it with this interpretation of Max Born. Okay, the fact that now once you find the solution to that equation, you're going to normalize it first. Otherwise, you're going to be dealing with nasty integrals every which way. So it's best to normalize the function itself. Once it's normalized, then finding the different probabilities becomes easier. It's just a matter of integrating and doing calculations. I'm saying the word easier in the broad sense, because it's really not that easy to solve Schrodinger's equation. Only for special cases when you can do it, okay? So one of those special cases, again, what we're going to tackle right now is a particle in a box. So we're going to do that problem and solve it and see how we're going to do that, okay? Because it's going to be helpful for us for what comes next. So the first example that we're going to do for is a particle trapped inside a box. Particle in an infinite box. So here is the situation. You have a particle, it doesn't matter what that is, and it's inside an infinite box. That means that the potential energy, I'm going to take this one x equals to 0 and this one x to L. So the box has a width L. And the potential in here is infinite. So here V goes to infinity. So I'm going to call it V naught goes to infinity. And in the same time, V naught equals to infinity in here, goes to infinity. And in here, V naught is exactly equal to 0. So the particle is trapped inside this box, basically. It cannot escape it, because in order to escape it, it needs an energy that is greater than infinity. And you don't have that. So it's trapped inside this box. So we want to find the wave function that satisfies Schrodinger's equation. So Here is the wave function again. It's I times h bar times this derivative of psi. Okay, I'm sorry. Before I do that, let me rewrite this equation because it's kind of complicated the way it's written in here. We're going to write it for a special case, okay? Here is the equation. So we're going to write it in the following fashion, okay? We're going to, hold on to this, okay? We're gonna come back to it, okay? Because I was going to write it with the space and time, and that's gonna be hard, okay? So we'll come back to the particle in box. So the first thing in here is the stationary states. Okay, so what I mean by that is solutions of psi, because all I have in here is just the derivative with respect to time in Schrodinger's equation. So I'm going to deal with that part first. So I'm going to assume that somehow the function psi, which is a function of x and t, looks like psi, this is lowercase psi, by the way, of x times an exponential factor that involves the energy. So it's going to be minus I E t over h bar. Okay, because if I take the derivative of this expression with respect to psi, basically what I did was I absorbed all of the temporal behavior in this exponential function. I'm going to make the use of the fact of Euler's expression, cosine of theta plus I sine of theta is equal to the exponential of I theta. Do you guys remember this Euler expression somehow? Yes.
I don't remember that one.
Did you guys use it in physics too at all, or math? Anybody?
It
I
looks a
didn't.
little familiar.
Okay, let me give you okay. Okay, so let me give you a hint into how you get this expression. You do a Taylor series of this term in here, and the Taylor series is simply 1 plus this number divided by a factorial of 1, so on and so forth. So it's going to be I theta divided by 1 factorial minus, because you're going to square this term in here, so you're going to put I squared, which is a minus theta squared over 2 factorial plus, again, when you cube it, you're going to end up with an I squared times I, which is going to be a negative theta cubed over 3 factorial and so on and so forth. So this is how Euler came up with it. The fourth term is going to be I to the power 4, which is just 1, because remember I squared is equal to negative 1. So when I take it to the power 4, it's going to be just in the plus 1 theta to the power 4 over 4 factorials. This is basically, continue this Taylor series. The cosine in here, when you do its Taylor series, it's 1 minus theta squared over 2 plus theta to the power 4 over 4 factorial and so on and so forth. And that the sine theta will be just theta minus theta cubed over 3 factorials and so on and so forth. If you identify term by term, you will see them appearing. Here is the cosine, and here is the sine, theta over 1 factorial, theta cubed over 3 factorial, except you have an I in front of it. So that is basically the proof for it, okay? It's based on Taylor. Make sense, Maddie?
Kind of.
Okay, honestly, if you have never seen the expression, it looks unfamiliar to you guys, but it's one of the basic expressions that is known in mathematics. As a matter of fact, it leads to one of the most fascinating equations. Let me tell you what that is, okay? So we're sidetracking from our topic, but it's worth it, okay? Because it's good to know this relationship too. Put theta equals to, what is it, pi over 2? Doesn't matter, put it pi, if you like, okay? Put it pi. Well, cosine of pi is equal to negative 1, and sine of pi is 0. So on one side, you have e to the I pi is equal to negative 1. Move negative 1 to the other side, and you have one of the most beautiful mathematical equations that you have ever seen in your lives, okay? Google it. 0, which was invented somewhere in the East by the Arabs. 1, which is a basic number in the numerals that was actually imported from the East also. Pi was known to the Greeks. I was invented by the Western culture later on. And E also the same thing. This is an equation that mixes East and West, brings all the numbers together, binary numbers and decimal numbers, complex numbers, pi, which is an irrational number, with its E counterpart. So this is an equation that combines everything in it, okay? Coming from this expression. So this is for fun. But the reason why I'm saying that in here is because we need it. We're converting this wave, which is inside the cosine and sine, into the exponential using Euler expression. So if I take the derivative now with respect to I h bar times the derivative of the big psi with respect to t. Well, the only place where I have t in here is coming from this expression. So I take the derivative of the exponential. It's easy. Then all I have to do is drop negative IE over h bar. So first of all, I have I h bar times negative IE over h bar times the rest of the stuff, which is psi itself in its full glory. Meaning you have the time-independent parameter plus times the exponential. So the equation then you end up with is the following in this case. First of all, then the I times the negative I will become just 1 because negative I squared is just 1. And that's why you have the negative in here. To make this one is 1. H bar and H bar cancel. So on one side you have E times psi is equal to negative. Okay, let me write psi again in its regular form, because in its combined form. The reason why I'm saying that is because I need it. I need to cancel that exponential from both sides. So on one side it's a little psi. That's how you write psi. It's little psi times the exponential of negative IE t over h bar. On the other side of the Schrodinger's equation, you have negative h bar over 2m times the second derivative of big psi with respect to x. But the second derivative of big psi with respect to x is nothing but the second derivative of little psi with respect to x. And it's straight derivative, by the way, because little psi depends only on x. And the exponential doesn't have an x on it, so I'm not worried about that. So it becomes negative h bar squared over 2m times the regular derivative of little psi with respect to x plus times the exponential, of course, of negative IET over h bar plus u, which only depends on x, times little psi, which only depends on x, times that exponential of negative IE t over h bar. So we separated the time and the space behavior of this equation. Now I cancel with respect to the exponential. The exponential can never be equal to 0, so I don't worry about it. So Schrodinger's equation then becomes the following: negative h bar squared over 2m times the derivative of psi with respect to x plus u of x psi of x, where this psi is a little one. Psi depends only on x, is equal to E psi, where E is my values for the energy now. This is the total energy. The point being in here is once we find the little psi, all we have to do is multiply it by the E, and now we have our psi that we need to normalize. Okay, so this is called the time-independent Schrodinger equation because psi now is just a function of x. And this is little psi, not that big psi that I was worried about it. So if you're trying to find the big psi, all you have to do is just whatever you find from this equation, multiplied by that negative exponential of IET over h bar. So this is basically what we need to do. So this is the time-independent Schrodinger equation. Okay, and this is the one that most of the time we deal with for this case. But once we find the energy that is coming from this expression, we're going to plug it into this expression. Now we have found the full-fledged psi, which is both, that depends both on t and x, because this is its spatial dependence, and the temporal dependence is expressed into this cosine and sine function as expressed by the Euler expression. So now, let's go back into the particle in the box. Does this make sense to you guys with this separation of variables? This is called the separation of variables. So basically, we took the time by itself into this exponential, and we left the space into the little x and the little psi, and we worked our way using that method. We cancel the exponentials, and we ended up with an equation just for psi itself, little psi, which depends only on x. So that partial derivative becomes just a regular derivative. That's all, because psi doesn't depend on anything but the x itself. Make sense? Okay, so now we're living in a space in a place where we can now do the particle in a box. So let's go back to the particle in a box again and try to describe it. So again, you have an infinite well. But the potential here is not equal to some value, but it goes to infinity. Except somewhere where the particle is trapped, where the potential actually is equal to 0. I'm going to write it to you now. In other words, this is how the function u of x depends on x. It's equal to infinity when x is less than 0. And it's equal to 0 when x is greater than 0 but less than L. This is x equals to L. And it's equal to infinity again when x is greater than L. So the particle now inside a place where the potential is 0, that means we have a free particle in here. Make sense? And in here, we should not really have any particle because it doesn't have enough energy. It will never have enough energy to climb that wall. Okay? So the particle is trapped inside the box in here. So this is a particle in a box. I mean, we call it a box because we imagine we're going to have a 3D version of this one. So this is the 1D version of it. So here is the situation then. Psi, the particle cannot exist on this side. So psi must be equal to 0 on this side, and psi must be equal to 0 on the other side. Psi in here can be anything you like, okay? That we need to find. Because Schrodinger's equation is of the second order, it's the second derivative in here. The second derivative is the difference between these two quantities. That means that its first derivative must exist and be continuous function too. So that means that psi or d psi with respect to x must be continuous in general, okay? Not in this case, okay, probably. And psi itself must be continuous because of the fact that we have to have a first derivative in order to have a second derivative. So we're going to impose a condition of continuity in this case on this function psi at both x equals to 0 and x equals to L. Now, here is how the equation looked like. We're going to focus inside the box. Inside the box, this is the equation. It's this equation except u equal to 0. So the equation looked like this, minus h bar squared over 2m. The second derivative with respect to x of psi is just equal to e psi. This is for x greater than 0, but less than L. For outside, psi must be 0. For x greater than L or s less than L, x less than 0, this equation gives me, we must have psi equals to 0 because we should not have a particle because it will not have enough energy to exist in this place because the potential is there. It's like a barrier, like a physical barrier, really, okay? If you take a tennis ball, for example, and put it inside a container, no matter how much you move it around, even if it has so much kinetic energy, it will not climb this wall. Even if it has a lot of kinetic energy trying to climb the wall, but because the wall is infinite, so it will never reach it. So that's basically what we're saying in here. And this is the same similar fashion. Well, E is a constant, that's the energy of the particle. It's constant value in this case because conservation of energy. So in this case, what I'm going to do in this case is write d squared of x, d squared of psi with respect to x is equal to minus 2me over h bar squared times psi. This is similar to a mass spring system. If you guys remember, the force, which is ma, and ma is the second derivative of the displacement with respect to time, is equal to minus kx squared, kx, I'm sorry, the displacement of the spring times x. So this is the mass spring that you saw in physics 1. Then you say the second derivative of x with respect to time is equal to minus k over m times x, and solution in this case is just a cosine and a sine function, where you have some factor, in this case a cosine of square root of k over m times t, because this is with respect to t, plus b times sine of kx square root of k over mt. This is the same fashion, except now instead of taking the derivative with respect to x, with respect to t, we're taking it with respect to x. So this is also a solution that is exhibits the same behavior, except with respect to space, not with respect to time. In other words, there is a constant a times a cosine of square root of this number, which is 2me over h bar squared, times x, plus b times a sine of square root of 2me over h bar squared times x. The way you find a and b in this situation is through the initial conditions. You impose at t equal to 0, what x was, x of 0 was, when you take a mass and you move at a certain distance, starts to oscillate. So that's your x naught displacement. And also, what was its velocity, which was the derivative of x with respect to 0, with respect to t at t equal to 0, and that is your v naught. So if you give it a kick, also it's going to move back and forth. So in a similar fashion, we don't have that in here. We don't have, first of all, temporal behavior. The temporal behavior was absorbed already in that exponential. But what we do now, we have boundary conditions. Boundary conditions. And the boundary conditions are the following. Psi must be continuous. That means psi of 0 must be 0, because the particle cannot exist on this side. And psi of L also must be 0. And psi of L also must be 0, because the particle cannot exist on this side. So this is the boundary conditions that we have to impose on this function. Does this make sense to you guys? First of all, if you take the derivative twice, and this is, we did it at least 2 times today, you're going to end up with a minus this number squared, which is this one, times psi itself. Does this make sense to you guys? Yes? No?
Kind of.
Okay, if you take, we did that, this is, if you take the derivative once, you're going to pull a square root in here, okay? And this will change sign, and this will keep its sign. This will become a sine, this will become a cosine. If you take the second derivative with respect to x, you're going to take another square root times the square root, so it's going to be 2me over h bar squared. And since this one already changed sign and became a sine, now it becomes just a cosine. And this will again, it become a, so it was now changed to a cosine. You're going to pull another square root, and the cosine becomes a negative sign. And you're going to take the negative of this square root squared, which is exactly what we need in here, negative 2me over h bar squared. And then you'll find the same function psi. So by substitution, you should be able to convince yourself. Try it by substitution. Okay. So if we impose these conditions now, what is psi of 0? Well, that should be x equals to 0 here. That means a cosine of 0, which is 1, a times cosine of 0, plus b times sine of 0 is equal to 0. Well, this is 1, and this is 0. B times 0 is 0, and a times 1 is 0. That means a is equal to 0. So a is 0. That is for sure. So this part of the derivative, you really did not need to concern yourself that much with. Now we need to find b. So in order to find b, we have to say size of 0, size of L is equal to 0, that means that A times, but A is 0, so we are not going to concern ourselves. We're going to focus immediately on B. So we have B times sine of the square root of 2me over h bar squared times L must be equal to 0. This is size of L. Must be equal to 0. This is inside the sign, by the way. Must be equal to 0. You have two possibilities. Either B is 0 or the sign of this thing is 0. If B is 0, you have a problem now because A is 0, and if B is 0, psi is 0, and you don't have a particle in there. Because if you try to find it, you're going to do this integration. Obviously, you're going to do it from 0 to L only, because from negative infinity to 0 and from L to infinity, psi itself is 0. You're going to find 0. Why? Because if A and B are 0, there is no particle. You cannot find it anywhere. And we know there is one. So B cannot be equal to 0. Since this integral is not possible, then B cannot be equal to 0. So the only thing in here is that the sign itself is 0. And if the sign is 0, that means its argument, it's either a 0 or a pi or a 2 pi or a negative pi or a negative 2 pi and so on and so forth. That means this thing is a multiples of pi. That means that the square root of 2me over h bar squared times L must be integer values of pi. That's it. N is an integer value. N can be 0 or plus or minus. 0 is not going to be acceptable, and I will tell you why. Okay, 1 plus or minus 2 and so on and so forth. Because if N is 0, that means the energy from this expression, which we are going to find, by the way, if we square this expression, is going to be 2me over h bar squared times L squared is equal to n squared pi squared, which means that the energy itself, E, depends on that integer n. So E depends on the integer that you choose for n, which is going to be n squared pi squared h bar squared over 2ml squared. So this is the energy that we found, and depends on an integer n. We cannot find n, we cannot have n equals to 0, because if n is equal to 0, that means E is equal to 0, and we're back to a solution that doesn't exist, because A is 0 and this term is 0, and we're back to the particle that doesn't exist. So n should not be equal to 0. So this is not a choice, really. So the only choices for n are plus or minus 1, that's fine, plus or minus 2, and so on and so forth. Okay, but not 0. As a matter of fact, yeah, so those are the values that are allowed for the energy n. In this case, it doesn't really matter because n is going to be 1 or 4 and square diamond and 9 and so on and so forth. Okay, so here is how the energy levels of this particle look like in here inside this box. For n equals to 1, this is the lowest energy value, which is pi squared h bar squared over 2ml squared. For n equals to 2, it's 4 times this number, 4 times pi squared h bar squared over 2ml squared. For n equals to 3, the distance now is at 9 times pi squared h bar squared over 2ml squared. So energy is quantized. It comes in discrete values. So the energy is quantized. And for each value of the energy, you will have a specific value for the function psi. You will have a specific value for the function psi. So again, A is 0. So B now is going to be equal to, so the function psi itself, which depends on this integers now, n, which is a function of x, is equal to B times a sine of the square root of this number divided by that. So it's going to be what? 2m times divided by h bar squared. So it's going to be n pi. What is it? 2me over h bar times x. So 2me over h bar, so the whole thing under the square root. So it's going to be n pi over L times x. So it's going to be n pi x over L. So this is basically the different solutions, and they are all going to depend on that integer n now. So it's not one. We didn't find one. We found a bunch of them. So the function psi itself, if you really care about it, is going to be this bn's times the sine of n pi x over L times the exponential of negative I e. E is this expression in here, which is n squared h bar squared divided by h bar. So it's going to be an h bar only. So it's n pi squared h bar over L times t in here. Okay, so if you really want to write the whole thing, here is the thing though. This bn, we need to find them. So these are called eigenstates. What I mean by that is, for each n, I have a solution. For n equals to 1, I have a solution. For n equals to 2, I have a solution. For n equals to 3, I have a different solution, different wave function, basically. For n equals to 1, the solution is just sine, but I need to find this bn's. And the way we find this bn's is to go back into the normalization condition again, because we know that the particle exists somewhere. So if psi is equal to psi 1, then in this case, it's going to be that term. So we're going to solve it in general. So if psi is equal to psi n, so what we're saying in here, the integral from 0 to L only, because I'm assuming the particle doesn't exist from negative infinity to 0 or from L to infinity. So the only thing I'm going to say in here is square this bn. So it's going to be bn squared times, because this is its own complex conjugate. This is actually a real number. So when you take its complex conjugate, it's going to be the same. So you're just going to multiply the function by itself, sine squared of n pi x over L dx must be equal to 1. This is a normalization condition. That means we know for sure the particles exist somewhere. Obviously, bn is a constant, so it's going to take it out of the integral, and you're going to integrate this expression from 0 to L. For that, you make you do a variable change where you're going to make y equals to n pi x over L. That means that the integration is from, first of all, when x is equal to 0, this term is going to be 0. When x is equal to L, this term is just going to be n pi for y. And then the variable dx, of course, is going to be L dx over n pi. Okay, so what we ended up with in this case is the integral from 0 to n pi. And then you have bn squared. And then you have this term in here, which is L over n pi times the integral of sine squared of y dy is equal to 1. Okay. You do the condition that sine squared, or 1 minus 2 sine squared, is equal to just sine of or cosine of twice y. And basically you end up with the term that this term in here, sine squared of y, is equal to 1 minus cosine of 2y divided by 2. This term will be 0. Because once I integrate the cosine, I end up with a sine. So then the integral of a negative cosine is actually going to be, so let's focus on term by term, because we're going to sub this value in here with this expression. So the integral of cosine part in here is going to give me 0, because it's going to end up with a sine of 2y divided by 4. The reason why 4 is you have a half, and you're going to have another half in here coming from this term. So integrated between 0 and n pi. Sine of 0 is 0. And sine of 2n pi, no matter what n is 0. Sine of 2n pi, no matter what the n is 0. Minus sine of 0, which is 0. So this term is going to give me 0. So the only thing I'm left with is the integral of 1/2 between 0 and n pi, and that is n pi. Okay, there is a problem in here. I think I may have made a mistake somewhere. I need to check on this last expression here for the boundaries when I did the change of variable in here. We need to verify this expression, okay? I think I'm trying to rush this thing at the end. Okay, I think there is a mistake in here. But at the end, this is true all the time. You're gonna find 1/2 in here, okay? You should have 1/2 in here. You should have 1/2 in here. Anyway, let me stop in here because I think we're running out of time anyway. And next time when we meet, I need to fix the normalization of this function. We have to find a solution for it. Once we find that, then we should be in business. Then we should find all of the different eigenstates, or the different how should I say, the functions that satisfy this equation. Okay. And then the actual solution is going to be a combination of all of them, which is something you cannot do in classical mechanics, because these are waves. They can interfere and make different waves. So this is for the wave and the particle. So what we still have in this chapter are the following. Finish the particle in the box, then take the particle in a well, which is of a finite height. So it's not infinite height, it's really a finite height. The problem is going to be very hard to solve, but we should be able to get some insight into how the particle is going to behave. Then we're going to take a particle hitting a wall. Okay. If you take a tennis ball, for example, and throw it in the ball, you have two possibilities. If the tennis ball has tremendous kinetic energy that can overpower the wall, so it's going to penetrate from the other side. But if the wall is high enough and strong enough and thick enough, it should not. Okay, it bounces back. For quantum particles, you will see that no matter how wide the wall is, on how strong it is, the particle always will end up on the other side. It will have a non-zero value being on the other side, not end up. Okay, it's called quantum tunneling. So we do this too, and then we're going to take the case of a particle inside the harmonic oscillator again, but from quantum mechanical perspective. Okay, so this will end up chapter 40. So with these things, we will finish chapter 40, and we will be in chapter 41. We'll take the same problem, but we will tackle it in 3D. Sometimes I rush things. Please let me know if things are not clear, and because things are getting a little bit complicated. So please let me know so that we explain them and we do examples with them. Sounds good?
Yep.
Sounds good.
And I apologize for going 2 minutes over, or 3 minutes now over time. Okay. And let me stop recording, and I'll see you guys Thursday. I'm sorry.
Have a good day, Professor.